All right, we've already looked at horizontal projectiles, and so that, is a projectile that starts out initially going horizontal and then, curve down because that's how projectiles work with gravity. Today we're going to look at angled projectiles, and the only difference between a horizontal projectile and an angled projectile is this initial direction. So with an angled projectile, you're either starting by going up or by going down slightly or significantly. And it works out pretty similar to what we were doing before. The difference is whatever your initial angle here is, you can find, and you have your initial velocity, you can find v naught cosine of theta, and that will give you your vx, and your vy will be v naught times sine of theta. And that's assuming that they give you this angle kind of here. Excuse me. If it's a different angle, if they give you something else, it's usually going to be this, but on occasion they might give you something weird like that angle. But, just draw a triangle, break it into components. And then it's exactly like before, where we know what's happening in our x direction, we know what's happening in our y direction, and then we just do some kinematics with it. Let's take a look at two examples, and hopefully that should help make things clear up. So for example 1, a ball is kicked with an initial velocity of 16 meters per second in the horizontal direction and 12 meters per second in the vertical direction. At what speed does the ball hit the ground? For how long does the ball remain in the air? What is the maximum height attained by the ball? So there's a lot of parts, but let's start by just sketching this situation. So we have our initial velocity, which they don't actually give us the initial velocity. Instead, they give us the initial velocity in the x direction, and that equals 16 meters per second. And notice that this vector drawing that I'm doing with these components, this is just a drawing of the velocity vectors. I haven't put distances in here, I haven't put anything else. It should just be velocity. Because when we're dealing with vectors like this, we want to just work in this context. Now, I'll draw a separate diagram here to show what happens with the ball over time. So it goes like that, and so we don't know our delta x, and we actually don't care about delta x. What we care about is the change in time. We care about the change in height here, so delta y, and I'm going to call that max. So I'm going to give that a subscript m. And we care about the final velocity. Now, we also know at the end, if it's going to hit the ground, the change in height should be 0 meters. So let's work with some kinematics equations here. So we want to find at what speed does the ball hit the ground. Well, we know the x speed isn't going to change. So Vx initial is going to equal Vx final is going to equal 16 meters per second. Because we're in projectile motion, we're in free fall, nothing changes in the horizontal direction. It doesn't speed up, it doesn't slow down, it just keeps a constant speed. But we don't know the final y velocity, but we do know the acceleration, which I'll add back up here. So we do know that the acceleration is g, and I'm going to call that negative. So we're going to have our down be negative and our up be positive. So we do know the acceleration, we do know the initial velocity, we're trying to find the velocity, we know the change in height. So we're going to say Vy squared equals V initial y squared. We have an error here, I just realized. Let me fix that. These should be initial velocities, so let's fix them. So V naught x and V naught in the y direction. So coming down here, we have our v naught, our vy squared equals v naught squared plus 2a delta y. And we know that the delta y is 0. Should be 0 meters per second squared. We know delta y is 0. So that whole term cancels out. So we get the final velocity in the y direction squared is equal to the initial velocity squared. The only difference is that means that our final velocity is going to be negative 12 meters per second. And I know this kind of just by looking at and thinking about the problem, that it's not going to be positive, it's got to be negative because it's going to be coming back down. So we've got our final velocity in the y direction, we've got our initial velocity in the x direction, or our final velocity in the x direction equaling 16 meters per second. So what is our final velocity? It's just the hypotenuse of this triangle, which this is a 3, 4, 5 triangle times 4. So that means, I believe this should be 20 meters per second. So v is 20 meters per second. So that's our final velocity. Again, we solved for the final y, we solved for the final x, and then we used the Pythagorean theorem to find our hypotenuse. Okay, so part B, how long does the ball remain in the air? Well, we need to solve for a t, and we could do that with my y direction stuff, but because I found the, yeah, we will have to use the y direction stuff, sorry. I thought we had the distance, but we don't. So, if I'm going to use my y information, I'm going to start with this kinematics equation. So delta y equals v naught y delta t plus 1/2 g delta t squared. Delta y we know is 0, again because it's landing on the ground where it was kicked from. V naught y we'll figure out in a minute. So then if we're going to solve this, we need to use our quadratic formula. So delta t is equal to negative of the b term, so negative v naught y, plus or minus the square root of v naught y squared minus four times a times the c term, so that will be and then times delta y divided by 2 times 1/2 g. So we'll check it, negative b, great, plus or minus the square root of b squared minus 4 times a times c divided by 2a. This term again goes to 0 because of the delta y being 0, so delta t equals negative v naught y plus or minus the square root of v naught y squared divided by 2 times 1/2 of negative 9.8 meters per second squared. And we're going to get a delta t equaling to negative v naught y plus or minus v naught y divided by negative 9.8 meters per second squared. So this will either equal 0 or 2 v naught y over 9.8. And I should have left that as a G, but you get the picture. So we get two answers, and this makes sense because when will it have changed no height? Well, either at the initial time when it hasn't moved, or after, it's flown through its path, so we should get a different time. I'll let you calculate that out on your own. And then lastly, for part C, we know that when it's at its maximum height, it should have no final velocity. So we're going to have v squared equal vy squared equals v naught y squared plus 2a delta x, delta y. This v is going to be 0, so that will mean we'll get that 2g delta y, negative 2g delta y, equals v naught y squared. And that means that we have v naught y squared over negative 2g should equal our delta y. And I'll also leave that as a calculation for you to run through if you want to find the final response.